Chapter 6, Grounding. A ground is a conducting connection between electrical circuits or equipment and the earth. Grounding electrical systems protect equipment by ensuring that the maximum phase to ground voltage is not exceeded. Article 250 covers grounding. Upon completing this chapter, you will be able to describe common reasons why electrical systems are grounded, define common terms associated with grounding, list considerations in determining whether AC and DC systems are to be grounded, describe grounding requirements for separately derived systems, describe grounding requirements for generators, list principal grounding requirements for equipment and enclosures, identify principal grounding requirements for fixed equipment, list common requirements for a grounding path and describe the principal grounding methods. Explain common bonding methods, contrast main and equipment bonding jumpers, list principal requirements for a grounding electrode system, identify principal requirements for grounding electrode conductors, identify principal requirements for equipment grounding conductors. New in the 2014 NEC, revised requirements for protection of ground clamps and fittings, clarification of grounding service supplied AC system requirements, new exception for supply side bonding jumpers, new exception for system bonding jumpers installed at multiple locations, revised requirements for buried grounding electrode conductors, new provisions for bonding in hazardous or classified locations, new table added for supply side sizing provisions. Grounding electrical systems protect equipment by ensuring that the maximum phase to ground voltage is not exceeded. Electrical systems are grounded to ensure that a low impedance ground path for fault current is present. Ground is the earth. For many years, ground was defined as a conducting connection between electrical circuits or equipment and the earth. Grounded is connected to the earth or a conducting body connected to the earth. A grounded conductor is a conductor that has been intentionally grounded. The grounded conductor can be a system conductor or a circuit conductor. The grounded conductor is commonly a neutral conductor. Not all electrical distribution systems, however, use the grounded conductor as a neutral. For example, corner grounded delta systems contain a grounded conductor that is not a neutral conductor. Therefore, it is incorrect to refer to all grounded conductors as neutral conductors, although that is the case in a majority of electrical distribution systems. An equipment grounding conductor is an electrical conductor that provides a ground fault current path. It provides a connection between the normally non-current carrying metal parts of equipment to the system grounded conductor, the grounding electrode conductor, or both. This connection usually occurs at the service equipment or at the source of power, such as a separately derived system, and helps to ensure the operation of the overcurrent protector device when fault conditions occur. The equipment grounding conductors may be in the form of a separate wire, metal conduit, metal tubing, metal cable sheath, etc. Equipment grounding conductors may also take on the additional function of bonding as described in Article 250, Part 5, Bonding. The equipment grounding conductor is connected to the system grounded conductor to facilitate the operation of the overcurrent protected device by providing a low impedance ground fault current path. This conductor is essential for life safety, yet most equipment can function quite normally with a poor equipment grounding conductor or even without an equipment ground conductor. A grounding electrode conductor is the conductor that connects the grounding electrodes to the system grounded conductor and the equipment grounding conductor. Like the equipment grounding conductor, this connection can occur at the service equipment or at the source of a separately derived system. The connection is only required to be made at one point on the grounding electrode system. The grounding electrode conductor may be constructed of aluminum, copper, or copper-clad aluminum, may be solid or stranded, and either insulated, covered, or bare per Article 250-62. The second condition under which the AC systems of less than 50 volts is required to be grounded occurs when the system is supplied from a transformer that is ungrounded. Per Article 250-20A2, the low voltage system is required to be grounded because the supply system is ungrounded. Section 250-20A3 requires AC systems of less than 50 volts to be grounded when they are installed outside as overhead conductors. Section 250-24A1 requires that the system grounded conductor shall be connected to the grounding electrode conductor at any accessible point on the load end of the overhead service conductors, service drop, underground service conductors, or service lateral up to and including the grounded conductor terminal in the service disconnecting means. For electrical installations which utilize parallel service entrance phase conductors, the minimum size of the grounded conductor is based on the total circular mill area of the conductors. For example, if three 500 kc mill conductors are installed in parallel, the total equivalent area is 1500 kc mill. Separately derived systems are a very common component of today's electrical distribution systems. A separately derived system is a system that supplies premises with electrical power derived or taken from storage batteries, solar photovoltaic systems, generators, transformers, or converter windings. See Article 100. By definition, a separately derived system can have no direct electrical connection to the conductors of the supplying system. This also applies to the grounded conductor. If the grounded conductor is solidly connected, then there is not a separately derived system. Ground references cannot be transferred through windings of any type. The grounding connection that were in place for the service must be re-established. Per Article 250.30A1, an unspliced system bonding jumper that complies with 250.28A through D is required to be installed between the equipment grounding conductor of the derived system and the grounded conductor. This connection shall be made at any point from the source of the separately derived system up to and including the first system disconnecting means or overcurrent protective device. The system bonding jumper shall be sized per Article 250.28D. It shall not be smaller than the size as shown in Table 250.102C1. For conductors larger than 1100 kc mil copper or 1750 kc mil aluminum, the bonding jumper is required to be not less than 12.5% of the area of the largest derived phase conductor. Per Article 250.30A5, for single separately derived systems, a grounding electroconductor is required to connect the newly established grounded conductor to the grounding electrode. This connection must be made at the same point on the separately derived system where the system bonding jumper is connected. In some installations, such as a panel board with main lugs only, the connection is made at the source of the separately derived system. The grounding electroconductor is sized per Article 250.66. Instead of basing the calculation on the size of the largest service entrance conductors, the calculation is based on the size of the largest derived phase conductors. If neither the steel nor the water piping proves to be suitable, other electrodes per Article 250.30A4, Exception 1, such as concrete encased electrodes, ground rings, or rod or pipe electrodes shall be used. No matter what type of grounding electrode is selected, it shall be as near as possible to, and preferably in the same area as, the point where the connection is made to the system. The frame of a portable generator is not required to be connected to the grounding electrode system. The frame is permitted to serve as a grounding electrode if two conditions are met. Per Article 250-34A1, the portable generator shall supply equipment or loads that are either directly connected to the frame of the generator or are cord and plug connected through receptacles which are directly connected to the frame of the generator. Per Article 250.80 exception, the use of a metal elbow to be used for underground non-metallic raceway installations without being grounded is permitted. The elbow shall be installed so that no point of it is within 18 inches of finished grade. Per Article 250.86 Exception 2, short sections of metal enclosures or raceways are permitted to be installed without being grounded. This gives relief from grounding of those installations in which the enclosure or raceway is merely used to provide support or mechanical protection. However, the term short section is not defined, and this could lead to confusion in the field and, more importantly, installations that pose a threat to life safety. Always check with the AHJ if there is any question concerning grounding. Here's an example of a short section of ungrounded EMT that provides support or mechanical protection through firewalls and is not grounded. Section 250.110 lists 6 general conditions where equipment which contains exposed non-current carrying metal parts and which is fastened in place or connected by a permanent wiring method shall be connected to the equipment grounding conductor. No specific equipment is mentioned. The requirements apply generally to all electrical installations. Section 250.112 lists specific equipment that shall be connected to the equipment grounding conductor if it contains exposed non-current carrying metal parts that are likely to become energized. There are no voltage limitations to these requirements. The following shall be connected to the equipment grounding conductor regardless of the voltage at which they operate. Grounding cord and plug connected equipment poses some design considerations beyond those required for fixed or fastened in place equipment. Cord and plug connected equipment is more susceptible to physical damage, which could affect the integrity of the equipment grounding conductor. One potential solution to this problem has been the advent of double insulated equipment, which in some cases can be used in lieu of a separate grounding conductor. Subsection 250.114 1-4 contains 4 conditions under which exposed, normally non-current carrying metal parts of a cord and plug connected equipment shall be connected to the equipment ground conductor. Electrical services are grounded by several connections that are usually made within or at the service equipment. The equipment grounding conductor shall be bonded to the grounded service conductor and the grounding electrode conductor per Article 250.130A. This section requires that all non-current carrying metal parts of equipment, enclosures, etc., which are required to be grounded, shall be grounded by one of 2 methods. The first method, given in 250.134A, permits the use of a recognized equipment ground conductor found in 250.118. 14 different listings under this section could be used as the equipment ground conductor for fixed equipment. For example, a piece of equipment which operates at 240 volts is fed by 2 ungrounded conductors installed in a 3/4 inch run of electrical metallic tubing. EMT is item 4 on the list and is permitted to serve as the equipment ground conductor for this circuit. The 1996 NEC contained a major change in 250.60. Frames of ranges and clothes dryers. Since the 1940s, the NEC had permitted the frames of ranges, including counter-mounted cooking units and wall-mounted ovens, and clothes dryers, to be grounded by the use of a grounded conductor provided all the following conditions were met. The supply circuit for 120 240 volt single-phase 3-wire or 120 208 3-phase 4-wire. The grounded conductor was at least a number 10 copper or number 8 aluminum. The grounded conductor was insulated, or if uninsulated, was part of an SE cable branch circuit originating at the service equipment. The equipment was bonded to the grounding contacts of a receptacle which is part of the equipment. The change no longer permits the use of the grounded conductor for this application. The change does, however, only apply to new branch circuit installations. New installations require the frame to be grounded per Article 251.34 and 251.38. Section 250.92b lists 4 methods that can be used to accomplish the required bonding for service equipment. The 4 methods that can be used for bonding of service equipment are: grounded service conductor, see Article 250.8, threaded connections. Fittings such as threaded hubs or bosses are permitted for bonding purposes when the fittings are made wrench tight. Threaded connections are commonly used with rigid metal conduit and intermediate metal conduit. Threadless connections were made up wrench tight for metal raceways and metal clad cable. Other listed devices, bonding is permitted to be accomplished by the use of bonding or grounding type lock nuts. Often overlooked requirements is the bonding of metal raceway and cable for circuits over 250 volts to ground. This section requires that electrical continuity be ensured by either threaded connections, threadless connection, bonding jumpers, or other devices. When the main bonding jumper is a screw only, it shall be colored green. This distinguishes it from the other screws on the grounded conductor terminal block. The main bonding jumper is attached by a green screw or exothermic welds, listed pressure connectors, listed clamps, or other listed means. See Article 250.8 for applicable provisions. The equipment bonding jumper is the conductor that connects 2 or more parts of the equipment grounding conductor. See Article 100. Like the main bonding jumper, equipment bonding jumpers are required to be constructed of copper or other corrosion-resistant materials. Section 250.102 contains the provisions for bonding jumpers. Where the size of the service entrant conductors exceeds 1100 kc mil copper or 1750 kc mil aluminum, the size of the line side equipment bonding jumper or main bonding jumper shall not be smaller than 12.5% of the phase conductors. If the service entrance conductors are run in parallel, the equipment bonding jumpers shall also be run in parallel. Unlike grounded conductors, equipment bonding jumpers, when run in parallel, shall be full-size conductors based on the largest conductor in each raceway or cable. Load side equipment bonding jumpers are sized per Article 250.102d and selected based upon the values listed in Table 251.22. The bonding jumper size is determined by the size or rating of the overcurrent protector device ahead of the equipment. If the equipment bonding jumper is to be used for more than one circuit in the raceway or cable, the size is selected from the Table 251.22 based upon the largest overcurrent protector device protecting a circuit within the raceway or cable. Bonding requirements have been added to 250.104c for exposed interior structural steel. If this steel forms a metal frame of a building, it shall be bonded to the service equipment enclosure, the service grounded conductor, or the grounding electrode conductor. This section applies to structural steel that is interconnected to form a metal frame. The provisions of this section do not apply to a steel beam supported by concrete columns. Section 250.24a and d, which details the grounding connection required for an AC service that is to be grounded, requires that the grounding electrode conductor be connected to a grounding electrode that complies with Article 250. Part 3 contains the requirements for the grounding electrode system. There may be buildings in which none of the electrodes specified in Article 250.52a 1 through 3 are available, or in which the only electrode available is the metal underground water pipe. In these cases, a supplemental electrode shall be installed. Section 250.52a 4 through 8 contains the requirements for made or other electrodes. An electrode is simply a means to permit current to enter the earth. Made electrodes can be designed to function much like the electrodes listed in Article 250.52a 1 through 3. As with these electrodes, made electrode connections shall be free from non-conductive coverings that may affect the impedance of the grounding path. Per 250.64e, the ferrous metal enclosures or raceways in which the grounding electrode conductor is installed shall be electrically continuous. This requires that both ends of the grounding electrode conductor enclosure be bonded to either the equipment or electrode or to the grounding electrode conductor itself. The size of the grounding electrode conductor is selected from Table 250.66 and is based upon the largest service entrance conductor per phase. If the service entrance conductors are paralleled, the equivalent area for a set of phase conductors shall be used as the base for sizing the equipment grounding conductor. The size of the grounding electrode conductor reflects, to some degree, the ability of the grounding electrode to dissipate current flow into the earth. For example, 250.66a, b, and c permit smaller size grounding electrode conductors for specific types of grounding electrodes. For sole connections to a single or multiple made electrode, 250.66a permits the grounding electrode conductor to be a number 6 copper or number 4 aluminum. The grounding electrode conductor is not required to be larger than a number 4 copper per Article 250.66b for sole connections to a single or multiple concrete encased electrode. For grounding rings, 250.66c permits the grounding electrode conductor, which is a sole connection, to be the same size as the conductor used for the grounding ring. For FMC, the fitting shall be listed for grounding, the circuit conductor shall be protected at not over 20 amps, and the total length of the FMC shall not exceed 6 feet. See Article 250.118.7. The 6-foot length limitation for all FMC, LFMC, and FMT relates to the total length, which includes any combination of these raceways in the same installation. For example, a 3-foot length of FMC and a 4-foot length of LFMC is the same installation. This is a violation. The equipment grounding conductors shall be run in parallel when conductors are run in parallel in multiple raceways or cables per 310.10h. Each of the equipment grounding conductors shall be a full-size conductor based on the ampere rating of the overcurrent protective device protecting the circuit conductors. See Article 250.122f. If multiple circuits are run in the same raceway, the size of the equipment grounding conductor shall be based on the largest overcurrent protective device protecting the circuit conductors, per Article 250.122c. If the circuit conductors are increased in size, similar adjustments shall be made in size of the equipment grounding conductor.